Standard car design relies on a load-bearing frame to support the engine and wheels. In Formula One, that frame is absent, replaced by an architecture where the drivetrain and the body are the same structure. There is no internal cradle or chassis rail holding the engine in place. The internal combustion engine and the gearbox are stressed structural members. They bolt directly to the rear of the driver's carbon fiber tub, forming the rear half of the car's physical spine. This eliminates the need for a rear frame, allowing the rear suspension wishbones to bolt straight onto the metallic casing of the gearbox. A Formula One car functions as a continuous aeromechanical platform. Its performance depends on three interdependent loops: the aerodynamic surfaces, the thermodynamic power unit, and the load-bearing drivetrain. Engineers must package over 1,000 horsepower and withstand tons of aerodynamic downforce within a structure that prioritizes extreme rigidity and minimal mass. Every major component in this assembly functions as a structural element of the chassis itself. The gearbox casing, cast from a magnesium alloy, absorbs the lateral cornering loads generated by the rear tires. It acts as the primary conduit for every force acting on the rear axle. The internal architecture of this 1997 Jordan F1 car reveals the lay shaft. This lower shaft receives rotational force directly from the engine. Rotational force transfers from the lay shaft to the gears on the main shaft. These gears spin freely and only engage the shaft when the driver selects a specific ratio. A pneumatic seamless shift mechanism fires selector forks across a central barrel to engage these ratios in milliseconds. These forks move dog rings, specialized collars that slide along splines on the main shaft to physically lock a spinning gear to the shaft. The teeth on these dog rings are machined with a specific undercut geometry. Under the load of 1,000 horsepower, this angled cut forces the gears and dog rings to pull each other tighter together, preventing the gears from slipping under high torque. The gearbox functions as both a power transmission device and a structural keystone that maintains the physical integrity of the rear assembly. Modern F1 performance relies on ground effect. This is an aerodynamic principle where the shape of the floor creates a massive low-pressure vacuum that pulls the car toward the track surface. To maintain this vacuum, the front wing cascades generate controlled turbulent air and direct it down the edges of the car's floor. This creates a vortex seal, an invisible barrier of spinning air that prevents high-pressure air from leaking under the car and disrupting the ground effect. If the chassis pitches forward during heavy braking, this airflow is disrupted. The vortex seal collapses and the car loses its aerodynamic downforce. This creates a conflict in mechanical requirements. The suspension must absorb track curbs for stability, yet stay rigid enough to maintain the precise aerodynamic attitude needed for ground effect. Heave springs resolve this by managing vertical compression. These central elements absorb the massive downward loads of aerodynamic pressure to prevent the car from bottoming out. Titanium and carbon fiber torsion bars provide lateral resistance. These rods twist under load to act as springs, strictly limiting how much the car leans while cornering at high speeds. The suspension system serves as a precision tool for maintaining the perfect 200-mile-per-hour vacuum required by the floor. The 1.6-liter V6 power unit is a closed thermodynamic loop. Waste exhaust gases drive both the turbocharger and the MGUH. The MGUH, or motor generator unit heat, captures thermal energy to keep the compressor spinning, which removes traditional turbo lag. The MGUK, or motor generator unit kinetic, harvests energy from the rear axle during braking and sends it to a centralized energy store. Manufacturing these internal combustion engine blocks requires specialized processes to handle the extreme internal temperatures of the hybrid system. Engine blocks are cast using robotic arms that print molds from synthetic sand. This additive process allows for cooling channels less than 2 millimeters wide to be integrated directly into the metal between cylinder bores. These channels manage the heat from HCCI, or homogeneous charge compression ignition. In this process, the fuel-air mixture is compressed until it is ready to ignite spontaneously. Despite using mandatory single spark plugs, the engine uses HCCI to burn excessively lean mixtures at high compression ratios, extracting maximum energy from a limited fuel flow. The power unit operates as an ultra-efficient thermodynamic battery, extracting joules of energy from exhaust heat and braking friction to supplement combustion. Cooling these systems requires constant iteration. The front brake assembly, where calipers and carbon discs can glow red with heat, is a primary area of focus for thermal management. Aerodynamic designers set the physical constraints for these brake ducts, often prioritizing the external airflow over the internal cooling requirements. Engineers use CFD, or computational fluid dynamics, to solve this. The software divides the duct's volume into tiny blocks to calculate precisely how air will move and how heat will transfer through the assembly. To move from digital designs to physical testing, a single duct may require over 60 individually 3D printed resin parts to manage the complex internal routing. These parts undergo ultrasonic resin washing and UV curing to ensure they are structurally safe for high-speed dynamometer testing. This design is restricted by an FIA regulation, stating that cooling air cannot escape through the outside face of the wheel. This requires hundreds of iterations for a single duct. Cooling the brakes is a necessity that cannot interfere with the critical aerodynamic seal of the car's floor. Reassembling the car highlights the structural dependencies across every system. The gearbox, suspension, and bodywork function as a single unit. There is an operational chain reaction between these parts. The efficiency of the MGUK determines brake sizing, which dictates the cooling duct design, which ultimately changes the behavior of the front wing vortices. A major regulatory constraint on this loop is the FIA's ADUO system, or Additional Development and Upgrade Opportunities. Because engine development is largely frozen, upgrades are rationed based on a manufacturer's ICE performance index. This forces teams to find performance within highly specific regulatory windows. Formula One is a zero-sum physics equation, where every component is structurally and thermodynamically dependent on every other.